I'm Bhavidhir V. Bharadwaj. Welcome to episode 51 of Genesis of Tomorrow. A very happy new year to each and every one of you. Today, we are having a conversation about quantum complexities, AI for science, and the future of physics with Dr. Dominik Kufel, who has his PhD in quantum science and engineering from Harvard University and is currently working as a researcher at periodic labs. Also, folks, if you're interested in such deep science and deep tech conversations and are able to derive even the slightest bit of value from the show, please support us by clicking the subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. All right, Dr. Dominic, there are quite a varied different matters about your particular field of working that I found very interesting. But to contextualize what you do for people who are turning in for the first time, what does thinking about physics particularly mean when you club it with artificial intelligence? There are computational terminologies like physics informed neural networks, so on and so forth, which are quite relevant and popular in terms of how they are thrown around. But what exactly does it mean to blend artificial intelligence and the idea of physics and even taking it a notch further, quantum research? And why do it all together at all? Like, is it curiosity? Is it a necessity, or is it maybe a blend of both? Like, how would you want to elucidate upon that?
Yeah, great. And first, thanks for having me here. And responding to your question, I think that so we've seen a lot of progress in AI in the recent years, right? Like sort of people seen the revolution of deep learning and all these sort of systems like AlphaGo and then like AlphaFold and more recently large language models. And then there's this natural question, right? Like if this is something which also can be helpful for physics itself, and in particular sort of quantum physics or things like relating a little bit to technology like quantum computing. And it seems that first these methods are already sort of finding some nice applications, and this is why one would want to study them. But the other thing is that if when we focus say on quantum computing, like when quantum computing like really comes to fruition and becomes helpful, it'll be like in an AI dominated world. So I find it personally sort of increasingly important to really think about these questions from the perspective of like AI, like how can we benefit quantum computing from the AI side, given the fact that like this will be the leading paradigm in the future where actually quantum computing like starts working out for practical problems. So this is, I guess, like one angle in this, and the other angle is also that um, to understand things like quantum computing and like really what is the genuine sort of like advantage we can gain from quantum computing. It's really the matter of like trying to push as much as possible like existing methods, like classical methods of simulation for quantum systems, such as, for instance, like artificial intelligence. And I have a feeling that in the last couple of years, there were many problems for which we did not appreciate, sort of AI enough, and we actually found out that like many of the problems which we hope to solve with sort of quantum computers turned out to be actually solvable to some extent with with AI. So this is definitely a personal interest, but at the same time, I think like a very timely interest as well. Both we start to see revolution right now, but also like it will be even more relevant, I think, in a couple of years' time. So it's good to understand the intersection as early as possible.
Diving a little bit deeper into your work, which was on approximately symmetric neural networks. Now, firstly, obviously, contextualizing that for the people, the viewers, but also something that I would want you to touch upon is how does this aspect of symmetry in physics at one end and the other end of the computational spectrum, neural networks, they coincide towards one another in some way or sort.
Yes, great. So I guess like just giving a very broad context, right? So what I'm mostly interested in, right, is like using AI for some quantum problems, in particular like some problems and sort of so-called quantum many-body systems, which sort of is the field which concerns itself with, for instance, like what are different phases of matter? How can we study them? Like how can we like realize them experimentally, and then how can we really utilize them to do some sort of useful technology out of it, like for instance, quantum computing or quantum sensing. So then, like within this field of like AI for quantum, one can approach a problem of, for instance, trying to understand if we can take a certain sort of like AI algorithm, like being just say I don't know a neural network, and then say okay, so this is a neural network which sort of captures the information about some quantum system, and then sort of we can think about okay, how can we really sort of design neural networks which are going to be able to like simulate quantum systems, and can they do that sort of efficiently, right? Like can we actually gain some new understanding of the quantum problem by sort of using these neural networks and applying them particularly to this problem we have at hand. And and the usual sort of conventional wisdom for problems and classical machine learning is that what you would do, right, like to improve the performance on a certain task, you would just like scale up the neural network architecture, right? So basically, that the bigger the neural network, provided like you scale up the data set accordingly, the better it will perform, provided like you push it like hard enough in a sense, right? And this is the progress we've got like in the last couple of years. This is like part of the reason why we get like so much of progress in like large language models recently, right? Because there's like this one simple recipe, which is just that if you want to boost the performance, just scale up the neural network. So now, what is interesting is that for some of these quantum physics problems, it turns out that this simple recipe does not seem to apply. So basically,
Hmm.
we seem to be having like some more complicated loss landscapes for like some of the physics problems we're studying. Also, we in many cases we have no data, and we instead
Hmm.
treat neural networks as just some objects which help us in sort of optimizing certain functions, rather than like actually having a genuine data set and then like caring about generalization. So it's a slightly different setting, and this setting makes it sort of quite a different problem where we just cannot benefit just from the scale, but we actually need to be a little bit more careful and sort of a little bit more clever in this sense, about how we're approaching these problems, right?
Hmm. Hmm.
So this is actually where where it seems to be a little bit of a grim situation, right? Like how do you really improve then, like if there's like no simple recipe? But this is also like where physics comes to be very helpful. The fact that when we model physics, we have certain intuition, and we have like certain set of like general principles about how to model something, right? So for instance, like in physics, there are many people who would agree with the statement that physics can be one of the most important concepts in physics is the concept of symmetry. So just
Hmm.
to give maybe a tiny example, right? Um,
Yeah.
a symmetry, right? Like it's just something where like some operation which leaves an object to be not changing, right? So for instance, like you take a square, you rotate it by 90 degrees, and it just looks the same as before, right? And basically it turns out that different phases of matter in physics can be understood as being classified in a sense through a notion of a symmetry. So for instance, like objects like liquids, they have some continuous translation symmetry for sort of various particles, and then solids, on the other hand, only have the discrete translation symmetry, right? Like the objects like form a lattice, and you can only like translate these particles by like a discrete vector. And in that sense, like, sort of we can classify, different phases, sort of like different substances, like by the symmetries. So this is like what's very important in physics, right? So now going back to neural networks, like, okay, so like how does like symmetry and a neural network connect? So it turns out that there's this like rich field within sort of general sort of AI known as like
Mm.
geometric machine learning. And this concerns itself with basically the study of like symmetries and like some sort of structure within the machine learning sort of algorithms or within the neural network architectures. And then it is pretty clear like how to sort of make neural networks to be aware of particular symmetries, and this is something which would benefit quite a bit in physics, right? Can you teach neural network sort of about certain symmetries within a neural network? You can, and like you don't even need
Mm.
like all this like geometric machine learning fuss. But like what geometric machine learning tells you is basically how to construct a neural network architecture such that automatically it will know about particular symmetries. So basically, like, you will give it, say, a simple neural network. You will give an image of a dog, and then like you will rotate the image of the dog by like 90 degrees, and then like neural network will still know that this is a dog and not a cat,
Yeah.
and it will know it by construction. So this is like what this very simple form of like geometric machine learning is about. So right now, like you've mentioned that this work of ours was involving approximately symmetric neural networks. So this is like one further layer of sort of abstraction here, and it's basically the recognition that for many practical problems in physics, we don't precisely know what is happening like everywhere, sort of in the search space, right? Like there exists like some points within the search space where we like know quite a lot about physics, and in particular we might know like that there are some symmetries present at these particular points, or like some lines or like some planes within this sort of like search space. But then the most interesting problem is actually away from these points where we know quite a lot.
Mm.
So this concept of approximately symmetric neural networks is really trying to, sort of, despite we're not looking into these like planes points and sort of and all that with like very simple structure and a lot of symmetries. For generic points, we still want to utilize these symmetries. And basically, approximately symmetric neural network is a prescription of like how to study these very general problems while still benefiting from the knowledge of these sort of points with a lot of symmetries. And
Mm.
then, from the perspective of these generic points, the sort of the neural network is only approximately symmetric, and symmetries are only approximate, but still, this is like what benefits the neural network construction. So then we've recognized that there is a class of problems in physics, and class of sort of exotic phases of matter, which we can very effectively study in this way. It turns out that the group of symmetries for them, like at these like special lines or like special points, is sort of exponentially large in system size. So this is something which is like quite remarkable and like pretty rare in like the usual sort of classical machine learning, the classical applications of like machine learning context, because in the usual context, right, like people would care about symmetries of a square, right? And like there are only like
Mm.
literally four symmetries, right? Like you rotate by like either 0 or 90 or sort of 180, right? Or 217, and that's it, right? So and here it's like actually much bigger group. So then we can actually benefit much more from the existence of these symmetries. So then we apply these models to these sort of like special classes of systems and physics. And what we are finding is that without pretty much like any extra computational effort, by incorporating this physics intuition, we can push according to a certain metric, like we can push the sort of the accuracy by like roughly 3 orders of magnitude, just by sort of imposing this like very simple physics trick. And so this is, I think, like one relevant lesson in here, that like unlike to a conventional machine learning paradigm, like it's not just about the scale, but it's also about like a certain physics intuition. And then it turns out that you can study pretty general models at these like interesting generic points in the search space, but yet with the benefit of like knowing some exact physics at like certain points in the search space. So this is the rough idea, and it's also something which turns out to be surprisingly powerful because you can then take that model, take these approximate symmetric neural network architectures, and then apply them to a variety of problems. For instance, like this is something which we use to study in detail the previously sort of like unobserved phase of matter, only like observed a couple of years ago in the experiment at Harvard and at Google, and
Hmm.
and then like showing actually something non-trivial about the experiment at Harvard, which people did not know about before, and we're really giving the very sort of quite rigorous and like quite high fidelity sort of intuition using precisely neural network approach for like what happened in that experiment, and like how can we generalize that and how can we optimize the future experiments on this topic.
Hmm. Okay, so to sort of summarize it all, we started off with you describing this sort of tug of war between scalability aspect of these computational models and the ability to interpret it all through data and whatever intuition that we want to instill into these models. Then we moved on to talking about geometric machine learning to sort of compound all these different facets that were laid out and funnel it all into this idea of not only making it about scaling the capacity of these models, but rather aiming the particular objective of our work to be instilling a physics based intuition into these. Is that right?
Absolutely.
Okay. So, right now I'm really trying to cater to a very quite a plethora of audience, like people who have background but also who do not. So, a very fundamental question at that then, physics, AI, both can inform one another, right? AI can inform physics in certain ways, and physics can inform the ability to build computational models in certain ways. What are, how does one differ from the other, and what are the current most bleeding edge advancements in both, and what are the sort of trade-offs or challenges that you face or the dead ends that you meet when you talk about these two spheres, sets which may be disjoint, which may intersect. I mean, for it's up to you to explain.
Yeah. So basically, yes, this is absolutely absolutely true, right? So there are many different aspects how we can look at like AI and physics intersection. The way I see it, like the one way of like categorizing them is sort of like sort of trying to use the advances of like AI to understand physics better, or like to try to control physics better, right? And this is sort of like one direction. The other direction is basically you will take some sort of like physics type of inspired methods, or basically some sort of new advancements in the field of say like quantum mechanics, right? To sort of then aid the sort of computation, and in particular some learning algorithms like sort of like machine learning. And so in terms of the former, like this is something which I guess like we could talk about like much more. The latter, I think it's like still pretty much like in its very early stages. So there's this field called like quantum machine learning, and this is the field which basically concerns itself with like trying to understand how we can take quantum machines and then like apply them to sort of solve some sort of like learning problems, like some machine learning problems in particular. And uh and if it comes to that field, there is a lot of sort of like confusion and so, but there's a very, very limited sort of evidence, as I understand, in terms of like how practical it is. There's a lot of stuff which is getting published in this, and there's like a lot of excitement and interest. But I think that this is still a very young field, and one really still needs to wait for the for that field to really be able to like beat state of the art sort of classical machine learning. However, for this, one can treat this problem even broader, right? So be thinking about, okay, so how can we reason and the physics way about like some AI systems, right? And then can this physics, sort of like reasoning about them be helpful for understanding the sort of the AI systems better? So in fact, like there are some sort of ways of trying to model like some of the AI sort of systems by thinking about like some physics concepts. So one very concrete direction I can give in that realm, which I think is promising, and sort of people should perhaps think a little bit more about this, is the following. So a couple of years ago at NeurIPS, right, like one of these top machine learning conferences, there was this paper on trying to understand, sort of when can you use like a certain type of a filter within a convolutional neural network, and like sort of like how large this filter needs to be to sort of be able to understand and like solve a particular sort of vision problem, right? So just a little bit of context, right? So convolutional neural networks are these special type of neural networks which are applied to vision tasks. So basically, like recognizing images and so. And there, like you'll have this object called a filter or a kernel, which you're going to like sort of like shift through an image, and then like sort of then train only the weights within that sort of filter. So then like instead of having like all to all connectivity as in the multi-layered perceptron, like you'll just look at the image sort of like somewhat more locally. And the main intuition is that if you want to recognize like certain features within the image, right, it is like local stuff which determines predominantly like what this feature is, right? So then like these little filters, right, like say like square shaped sort of objects with just like a couple of weights. There's a question of like how big these filters need to be. Like, do they need to span the entire system, like the entire image, or do they need to be like sort of relatively small, and so and so. So then this question, like, seemed to be, sort of answered in very practical terms only. Like people were like, sort of empirically checking, like if making a bigger filter, like actually increases the accuracy and so and so. But then there was this very interesting work I'm alluding to, which sort of studied the same problem from the perspective of sort of more of a physics-inspired method. And then what they've shown is that the size of this filter required for achieving certain accuracy is dependent on quantum entanglement of your data. So,
Okay.
so this is very, very peculiar, right? Like, how do you make this connection, and so and so. And just to give a very rough intuition about what's going on is that what quantum entanglement sort of captures is like some notion of a correlation within your system. And then like and then by studying this these sort of like correlations about like roughly how important is the point far away to like your point down here, right? Like by studying these sorts of questions, it turns out that then you can say like how non-local, like how large this filter needs to be, and then give actually very strict mathematical bounds for like certain not very idealized scenarios, like actually scenarios which are like pretty close to the downstream usage of convolutional neural nets, and then show that indeed like this is the distinction which people would be terming in condensed matter physics is like area law versus like volume law entanglement. So I think that this kind of a physics reasoning, like this example shows that this kind of physics reasoning can be helpful for like actually understanding some practical problems like in a classical machine learning realm. And I do think that this is like one of the directions which can be explored a little bit more, and it will be actually fruitful for like our understanding of sort of AI as a whole. So yeah, that's like one of the examples out here. Uh, Good. Yeah. So I guess, yeah, two main categories. Sort of AI for physics, or physics for AI. I think some of these physics inspired methods are very interesting, and in fact can be helpful for our understanding of AI in terms of like the usage of like new physics, like quantum physics, for doing the AI. As of now, at least, like I'm slightly more skeptical, but I think that this is just a very young field, which perhaps requires a little bit more time to like really come to fruition. And both the progress on the algorithm side and also the progress on the quantum hardware side, and hopefully down the line it will also be helpful.
I'll come back to this little. I've two, three, maybe more plausible questions that this struck me out from this description of yours. But holding my thought trail a little bit, how did it began for you? Because from whatever, no, surely you're far more of a veteran in the entire game of research, the part and parcel of research than me. But from whatever I've been able to viscerally or individually been able to gather in terms of how research works, it's a funnel that trickles you down your particular specific subject matter niche area of study over a time period, a designated time period. You start off with a larger area, and then it sort of cuts and cuts and cuts and cuts through till you have this very particular segment that you find yourself very, very, very inclined towards. Physics, quantum research, many body physics, so on and so forth, the computational interests and inklings, whatever there you might have had, how did that all subsided over the years from maybe your school days, high school days to undergrad, so on and so forth, to now you working in this entire domain of, AI scientist? We'll come to that as well. But maybe, yeah, it's just about that.
Great, yeah. Thank you for this question. Yeah, I think it's it's been for me like quite a an interesting story that first of all, maybe I should say that I'm a very young researcher, but like
Hmm. Hmm.
I'm
Hmm.
very sort of lucky to learn from some people I find like just sort of absolutely role models, and how to do research, and sort of like all the advices I had so far were like absolutely amazing, and and like all credit goes to them, like in terms of how I'm doing research. And explaining the story a little bit. So I started to do like research relatively early on, and I was sort of like born in Poland, and Poland, like we had this organization for like call it like gifted sort of students, where you could just like go and sort of do a tiny internship while still being in high school, like with like some research in academia. And then like this is what I did, and I actually started my work in like computational neuroscience. And that was like just some problem which was like still very physicsy, but like it was still about sort of the brain, and basically like how does temperature affect sort of the connections in brain, like in between neurons, like synapses basically. And and there we're studying how does the sort of like temperature change this sort of conductivity of the synapse as a function of time, as you are sort of like raising up or like lowering down the temperature. So this is like kind of the first project I've had, and this is also like the first paper I ever published, was like in this computational neuroscience field. And they're like it's still relatively related to sort of the artificial intelligence, right? In a sense of that, yes, like we're not dealing with artificial neural networks, but we're dealing with like biological neural networks. Like some of the concepts are similar. Like still you have neurons, still you have like connections between neurons, like still you're sort of concerned about like how these different signals integrate together, and and I was like in that sense similar. And then like I sort of moved for my undergrad to the UK, and there like I had a little bit more of a interest in sort of in like fundamental physics, and like really trying to understand like some how to find some new solutions to the Schrodinger's equation, and also like some topics in like applied mathematics, and like classical mechanics, and it was a little bit of like an exploration at that point. But at that point, like I also started to sort of pivot a little bit more towards condensed matter physics, because I've realized that condensed matter physics is like this kind of a place where there's some very concrete stuff you can do, like experiments, and also there's very concrete technology coming out of it, like things like a classical computer. The fact that we are able to sort of talk right now, right, like is the it's because we have computers, because we have transistors, because we have semiconductors, of which physics we understand only because we have quantum mechanics. So then, like there's all this like quantum mechanics building to solid state physics is like what brought us all this technological advancement. So then I got interested in like condensed matter physics, and I really wanted to understand like what are different methods how we can study condensed matter physics, like how can we really sort of make some progress into just like how can we understand new systems, etc. So then, like when I came to my grad school at Harvard, like my advisor sort of like said, oh, how about we sort of like look into this topic, which at time was like very underexplored, and that was the topic of like how can we use like neural networks to study these sort of many body quantum systems. And um and then, like initially I was quite skeptical about this, and I was like it seems to be a little bit messy, and like we don't understand these neural networks very well, and there are all these sort of like existing methods and sort of quantum physics for studying these problems, which are actually like much better founded at a face value. But then, like we started exploring this topic, and we started to understand that actually there is quite of perhaps like an intersection of like these quantum physics problems or quantum computing problems, and neural networks, or more generally AI, which really allows you to study some new stuff which cannot be tackled with any other method. And this is like our goal from the very beginning, that like we really wanted to say, okay, so here's the physics problem, and the method we're developing is the only one on the market which can actually sort of solve this problem, right? And we're really intensely trying to search for problem classes like well that would be true, and where these neural networks can really give us a benefit. And over the course of like the last 3 years or so, like we found some of these problems. So these ones include like what we already talked about, so these sort of approximately symmetric neural networks applied to these exotic sort of systems I've mentioned. But there are also sort of more things, it turns out, like sort of studying some problems which sort of some experimental problems where like you would have these so-called like NV centers and diamond. So basically like some platforms for like doing quantum sensing. And there it turned out that like all the other methods like do not seem to be like helpful in like studying these models, or they're like making some uncontrolled approximations. And then like with neural networks we can actually make some progress in studying these. So that's like another kind of an idea. And sort of like all that, I guess, like sort of brought us to really understand that like some of these AI tools will be and one of the indispensable tools in the future. And sort of made us to take it even more seriously, right? Like going more in this direction of like large language models and like an AI scientist and so on. So I guess that this is how it ended up. So with a lot of skepticism, I accepted that AI is something which is going to be helpful for studying physics, and it really seems to be panning out in a longer term.
Hmm. Your suggestion for the students nowadays, undergrad or PhD students, so on and so forth, who are working day in day out with physics to whatever degree possible, they may have that as something that they are just interested to learn about, or maybe as a formal coursework. In general, how would you recommend them to utilize artificial intelligence or computational methodologies to better be able to understand physics? Because one recommendation that I got from a friend of mine was that start coding physics. Because I come from a coding background, a programming, computational background. Physics for me was something that I was just interested in. But this lad, he advised me to start utilizing programming for visualizing these physical phenomena. Now that is tougher, and you got to work a little bit more harder for it to actually be beneficial and fruitful for you, but it pays off when you go through these phenomena and are able to realize them into this simulated reality, which is to some degree or the other mirroring the actual physical manifestation of those. You better understand how physically all these things work. May it be the working of an atom, why it spins at all, why does it spin like it spins, from that scale to maybe going on to cosmos and black holes, how gravity ruptures and stops over there, all these different aspects. How would you then suggest, again, somebody who's working with all both these things, AI, computation, and physics very much deeply, how do you suggest students to go on about utilizing computational means and artificial intelligence to deepen their understanding and intuition for physics?
Yeah, I think that this is a very timely question. It's definitely hard for me to sort of give advice on this because things are progressing so rapidly, and and it's really hard for me to say like what are precisely the skills which will be required to be sort of successful as a I don't know as a researcher, as a physicist, and so like in the next couple of years. But I do think that one of the things which is important is like really trying to take this computational side very seriously, right? And I do definitely agree with like what you said that sometimes you can study certain concepts in physics and then feel like they kind of like make sense, but like not perfectly. And then one way to test it, right? Like one thing which was like very helpful to me, like doing an undergrad and so was like, okay, do you understand a certain phenomenon, like a certain I don't know physics principle? Like try to really code up a simulation with it, right? So basically, like sort of try to think about, okay, so how would I like set up a certain code which is going to like prove certain hypothesis I have, and and this is like actually something which which I found like very helpful like during my undergrad and the and sort of on multiple occasions. Like just to give you an example, like I remember that there was this like one sort of problem in classical mechanics. Sort of I was testing like for a homework for one of the classes I took, and then like I was kind of bored with that task because it like felt very simple. But then I was like, okay, so can I, for instance, like sort of then try to extend that sort of simple problem and then like include certain extra effects, like say whatever friction or something, right? So then like it turned out that like by actually like sitting down trying to like code that thing up and like looking into how did how can you manipulate like some of the equations either in the analytical form or like in by constructing a numerical simulation, I was like actually able to sort of do something which was not previously well known solution, and which actually gave me like a lot of joy because first it tested my understanding, but it also like allowed me to study sort of things beyond the textbook in itself, and that was like something which was like certainly very very valuable. And that was like during my undergrad, which was like still a pre chat gpt era. And I think right now with like chat gpt and like other large language models, I do think that the barrier of sort of like entry into like simulating something computationally or to build a better physics understanding or like to do sort of like some little calculations you would normally like which would normally take you much longer time, it's actually right now like much easier with these methods, right? So I find it personally very very beneficial, and I'm, as I understand, I'm not the only one for like just sitting down and like trying to understand physics a little bit better by like chatting with like chat gpt, gemini, or like other models. And then like you just have a certain question or a certain intuition, right? And then you're like, oh, I'm studying this model, I'm trying to understand this better, like here's the tension I have in my head, like how do I really resolve it, right? And then like by going sort of like back and forth, you can really get more and sort of kind of better and better understanding of a particular topic, and you can really clear up like many of these like subtleties which are out there in your mind, and which normally you could also try to resolve by just like talking to other people. But at times when you just want to like study, sort of by yourself, like it's very, very nice to just sit down with, whatever large language model of interest, and then just, sort of like talk with it such that like you can, it benefits your own understanding. So like you want to avoid like, directly getting the answer, but typically for like more subtle questions, you won't be able to directly get the answer anyway. But then, you can just go and like, chat with it and then like refine the understanding and then like iterate multiple times. And then, it was useful to me like on numerous occasions to just, sort of go and do that, and like really just to solidify like very particular things given a certain context of like a paper or like, sort of like something else. So this is definitely what I would encourage as well, right? Like apart from just, sort of trying to, code this stuff up and like really, sort of benefit, sort of test your understanding in this way. I'd also encourage people to just sort of look into all these like large language models and like all these tools available, and then like try to use them as the learning tools, and really
Mm.
ask some curious questions, and then like iterate and really then like construct some nice understanding of this, even for like very sort of like new fields for you, right? Like you can go and for instance like um I recently was like sort of like hearing about like some I was listening to some talk on like quantum gravity, and I'm not a quantum gravity person. But then by sort of like first talking to ChatGPT and trying to understand like very basic concepts of like how do they map to the language of a condensed matter theorist, I was able to understand like what is the topic and like what is the mental model of like what this talk is about, given the the context like ChatGPT has given me. So this is definitely sort of something which I find personally helpful, and I think like people will also find it helpful. And in fact, I think in a couple of years' time, this will be like one of the indispensable tools, because this will be the best way and like the quickest way of like introducing yourself quickly to a particular
Mm.
field.
Mm.
So this is like another recommendation I would have.
Yeah. So that is partly the answer to also how do you get into or familiarize yourself to a new subject matter or field of study, or maybe any different pillar of understanding that you want to build or carve out. But sort of completing the answer to this, uh, research, the other thing with research is you run into these dead ends where you are by definition then required to take up new theory, take up new studies, fields even, and then learn them anew without having any context or prior background. You did answer that shortly how AI, these LLMs can help into carving out that basic preliminary sort of bedrock of sorts, but maybe a little bit more into what would be a better way towards, for a researcher, towards building a better foundational understanding of new subject matters that that become necessary for them to pick on to while they are trying to solve this particular problem.
Yeah, so I definitely don't have a perfect answer for this, but I do think that an AI right now like can be already quite helpful and trying to understand connections to other fields. Like, for instance, I can give you an example. Like, recently we've been thinking about like some problems, and again, this realm of like geometric machine learning, and so and these this application of these sort of neural network methods to quantum has like sort of like multiple different levels, and like some of it, for
Hmm.
instance, involves like some way of like constructing like optimal sort of Monte Carlo estimators for certain quantities, right? Which is sort of more of a domain of like statistics, or say like probability theory. And and these are subjects which I was obviously like trained on, but sort of I'm not sort of like doing a research on this like day to day, and then like there are plenty of papers written on this. At the same time, they're like written in a very specific technical language, and very often it takes like quite a while to like go through the paper and then like try to understand if this is like even the thing which you're interested in, right? So then like what I find AI quite helpful for right now is, for instance, like really trying to sort of chat again with like some large language model, and then like ask it questions like, oh, what are the methods which could be promising, then like give me links to these papers, and then like sort of I would inspect these papers myself and like try to judge like if they would be helpful or not. And then like sort of it's very nice because then like I can also ask a large language model to like translate this paper to the language I understand, and therefore like make things to be much more efficient. And this is very often, I guess, when you're doing research, right? Like there's some other fields which you know definitely heard of, but like you're not the best expert in. And this is like one way of like trying to mitigate this, right? Like you talk with a large language model, it tells you like, oh, these are the things like people would care about in this field, and like these are, I don't know, like whatever, some error metrics which you should like look into. And then based on that you can just sort of be much more efficient about sort of like pivoting slightly in a new direction by just sort of
Mm.
making connections. But then since you don't know the field, you wouldn't be able to make these connections yourself. But right now it seems that the large language model having like much more sort of like a vast understanding of the broad fields, it can really give you some sort of extra help in this. And yes, you still need to validate like what it's giving you. Like sometimes it might like hallucinate the connection, but I find it like more helpful, sort of well, more often helpful than not. So this is like one of the things which I think can help a researcher to like really get into the new field. Just like a curious like focused chat where you're not wanting to directly get the answers, but instead where you're really wanting to sort of understand a particular topic a little bit better and like make a connection, and then like try to make this connection to be like very precise. So I think that this is another way how AI can be helpful.
Mm. Mm. One other aspect, maybe the final one in terms of a researcher's journey, is how you set yourself apart as a unique asset to any research project or endeavor. And now that does speak to your individual capability and competence, but a large part is being able to actually show yourself as somebody who is different in this very big pool of researchers in whatever, from whatever background, whatever it be. How exactly in today's evolving, very fast pacedly evolving time, do you build your portfolio or your arsenal of sorts to show off your expertise or an expertise that you're building towards in a way that is able to actually differentiate you out of the entire crowd that is standing out there?
Yeah, so I'm not sure if I precisely know the answer to this question. I'm again like definitely trying to learn from some people which like personally like who personally impress me. uh but I think something which certainly I find personally important as how you actually present your ideas to the world, right? And really emphasizing this context of the fact that physics and AI like these are very collaborative fields, right? Like how do you share your ideas? Like how do you learn how to talk to someone like who might speak a slightly different language than you are, and sort of then really benefit from this sort of interaction of like two people who like might not be normally talking because sort of the sort of the barrier which is just the language, like different languages like each field sort of speaks. And this is like what I find personally very rewarding, right? Like the fact that sort of in my research I would be like talking quite a lot to like people working on some sort of on some machine learning, on like some material science, on some very particular topics in like quantum physics and so, and still somehow be able to find the common language and really try to understand like what is the right language to talk about something, right? Clearly you can have a lot of different ideas, right? And these ideas can be, each of them can be presented in like, multiple different sort of like, lights, right? Like pretty much like, there are so many different colors in which you can sort of dress a particular idea. And what color you dress this idea in like highly depends on the audience you're talking to, right? And it really seems to be, important, I think, in the current world where people are speaking different languages, where like multiple fields are, however, like very often talking about very similar stuff. It's really be able to like translate between all these different languages, and then like when you talk about your own ideas, also being able to talk about it, sort of in these very different sort of like contexts, and very different languages, right? So this is what I find personally sort of important, like the communication and the fact that, even if you have like the very best ideas, like you need to be able to like sort of communicate them well to like sort of a broad range of people. So I guess that this is sort of one aspect, and yeah, and I think, apart from that, just, sort of emphasizing the collaboration in itself, right? Like the fact that you would be talking to various people, and like how to talk to these people, and then like how to make yourself useful to them, in a sense of like, you provide them with like certain expertise. And so this is
Big
something which
time.
I think is very, very important as well, right? Like I know sort of some researchers, right, like who'd be absolutely amazing researchers in terms of the ideas they're having, in terms of how much progress they can do on like very challenging sort of math tasks and so and so. But then they would have a very hard time like really trying to make these sort of math problems they've solved to be helpful to the rest of the community. And in that sense, like they cannot have like a very big impact on that community. And I think that this is another important skill, like really trying to understand like how can I be useful, and like how can I really connect with these people, and sort of like try to use my some expertise I have to benefit someone else's sort of research directions. So I think that this is another important thing.
I believe yes, communication, and that too, relentless communication is a very very integral part, especially in the world that we live in today, where attention is commoditized to maybe the largest degree possible. And I mean, the best thing that happens if you keep on relentlessly communicating, even if you are not very good at it from the get go, is, well, the best case scenario, iteratively you become better with each epoch, and eventually you're able to get to an extent where you're able to convey not only your ideas but also the intent and the journey behind those ideas in a way that not only furthers the idea and the conception itself of it, but also your journey and your contributions in elevating the substance and quality of those ideas. Or in the worst case scenario, if maybe let's say your work is not potent for the next 10, 20, 30, 40, 50, 60, 70, 80 years even, because that every now and then does happen with individuals, your brilliance or your genius is not recognized or recognizable even in this lifetime, maybe, well, you'll become a sort of legend for the generations to come. That's the worst case scenario if you just continue communicating your ideas. But one aspect that I've vicariously seen a lot of younger folks at least fall into, and I think you'll agree with that, is the hesitation to look uninformed. People use the word dumb here, that they are scared to look dumb, but I think it's not that. It's a little bit more about being hesitant to look uninformed. They do not want to give off the vibe or the look that they have not done their due diligence. Would you have anything to say upon that?
Yeah, I think I totally agree. Like, you know, it is definitely the problem, not just for humans, also for like large language models as of
Oh
now.
yes. Hmm.
Like, as of like, the end of 2025, they're still very bad at like telling when they don't know. Um but then the same applies to humans, right? Like I agree, like many people might be, sort of afraid of like, sort of asking, well, quote, dumb questions. um, I do think that, you know, overwhelming majority of questions one might ask are not dumb in a sense of like, even if you're asking very simple question, but like a question which, sort of really, sort of like allows you to understand the very basic context of like how you can understand something, right? And then because of that, you'll be able to like, sort of listen to the speaker much more attentively because you have like a mental sort of model of something in your mind, which then allows you to like ask better questions and like really understand what the speaker is talking about. I mean, I'm pretty much like, I don't know, 95% plus sure that the speaker will be much more happy to answer, a couple of dumb questions and then like, have a, a listener listening much more attentively than, having a disconnected listener who does not understand what the what the person is talking about, right? So I think that this is definitely true, and I also see that in like many of the professors I would be working with, that like they're not afraid of asking these questions,
Mm.
and I think part of it, like why some people are afraid, is just that they're really afraid of like sort of looking down by themselves, right? Like,
Yeah.
and this is why like I guess one way of practicing it is just like asking all these questions in every single conversation you're having, right? Like not necessarily talking to like some people like you might be like fearing a little bit, but more about just like day to day conversations with friends and so, and just like trying to understand. And after a while these things like become very natural, and then like you're not afraid of like asking a dumb question like even to like a very important person. And then like things become sort of like much nicer because then you can feel that you can genuinely learn, regardless of like who you're talking to and so and so. So yeah, I highly recommend that, and I would be definitely one of these people who ask a lot of dumb questions.
I mean, a very good paragon example then how it does help. But okay, the final aspect that I would really want you to talk about is, can AI actually discover new physics or new scientific novelty per se, or will it continue to just be confined to pattern extrapolation? And where is it right now?
Great. So I think, it's interesting because a couple of months ago, if you asked me this question, I would be probably saying, well, probably not. In a sense of like, it does not seem to be that in a very foreseeable future, I can see these models to be sort of, good enough to actually like discover new physics.
Hmm.
But right now, like, after quite a, sort of healthy dose of skepticism, I think that it's not as insane as it seems. And in fact, right now I think like I do believe in the fact that we'll be able to discover plenty of interesting and new physics by using sort of large language models as a driver, right? So um so one of the things which sort of got me convinced about this is really that the progress and the basic sort of like LLMs is crazy, right? Like in a sense of like there were some evils in the past, right? Like some benchmarks and so like showing how better you can predict the next token, right? Like all these like perplexity evils and so. Then like switching to like some benchmarks, sort of math benchmarks, like some physics question or like a graduate level question benchmarks and so, and like we see just in the last year or so, we see the progress from like I don't know, like roughly 20% or so accuracy on these benchmarks to like 95% plus accuracy on these benchmarks, right? And and these are so this is like one aspect of this, right? Like which is just that the very basic models, like the flagship models we're having, their performance improves like so much over like such a short time scale. So this is like the first clue. The second clue is that these models, like we have not tried to tailor them to science very much, at least like so far, right? So by sort of trying to improve the models, I like really mean that they're not just reading through like the entire internet, but they're like then sort of looking through like some physics textbooks, like some sort of like whatever archive papers and so and so, and like really trying to like learn based on reading these ones again, and like really sort of like trying to like align themselves with the scope of being a scientist, right? And like really go through like certain sort of like specific papers, specific textbooks, and so and so. Like we're just barely starting to sort of like to train such models. So this is the second aspect, that like this thing we have not explored at all, and I do think that this is something which is going to be quite helpful. And then the third
Mm-hmm.
aspect is that very often people are talking about large language models in context of just like, oh, can it like sort of calculate like what is whatever 23 plus like 46 or something, right? And then people are like, oh, it made a mistake here, right? So then like it's obviously dumb because it cannot even like add two numbers. Like how can it make like sort of genuine scientific discoveries, right? I can assure
Mm-hmm.
you that like I would make similar mistakes if you gave me like enough of like computations like that. And then like how do I resolve it as a human, right? Like how do I resolve it as a scientist? Well, I have tools, right? I have tools like a calculator. I have like tools like a Python code where I can actually sort of take this sort of idea I have and then like sort of delegate it to a tool which is able to do that flawlessly, right? So this is what we're just barely starting to do. So we're just barely starting to construct these like agentic workflows with large language models, which have an access to like tool calling, and which have like access to like actually verifying its outputs, then like checking if these outputs make sense, iterating on them, and then like sort of doing this extensive tool calling to like I don't know Python or like some other sort of tools like whatever web search, etc., literature review, and so and so. And I do think that this is something where a lot of potential for solving scientific problems lies. And even assuming the current generation of like large language models, and assuming that these would not improve, which I don't, based on the point number one I've mentioned, I don't believe it's true. I think that they'll be, sort of still developing quite a bit, at least in the, very sort of short term future. Even if they were not sort of developing, then still I think that there's so much to do with like the existing models in terms of constructing the correct agentic, sort of expert based agentic workflows for a particular task, right? So by that I mean, for instance, like you have a couple of like large language models. It can be the same sort of model, just like copied, like say whatever GPT 5.2, which then you sort of put in the in the various parts of your workflow, and then you have a certain workflow, right? Like where you're asking, I don't know, a physics question, right? And then there's a certain procedure which is being followed, a certain scientific pipeline which you would normally do, like searching for the literature, like forming hypothesis, then like and this is like what one large language model would do. The other LLM would be like critiquing that hypothesis, and then like they would be like going back and forth like that. Then eventually you would be like sort of calling a certain Python code, right? Like which is going to like implement that hypothesis and test it. If that turned out to not be correct, then like you iterate back, and then like you do more literature search, you analyze the equations a bit more, and then like you do that back and forth until like actually you get the answer which is like self-consistent, or at least like sort of you can verify it in like some way. And then like by constructing these workflows and having these like specialized agents for like sort of a particular task, which are going to like communicate with each other, do extensive tool calling, do extensive verification, make a lot of smart trial and error, and then verify it. I think that we'll be able to make a tremendous progress on like at least like some specific problems within, I don't know, quantum physics, or most likely also some other fields. And this is something which is just starting. There
Mm-hmm.
are just a handful of works on this, a handful of sort of like directions people have, but already we know some examples of situations where For instance, like some model from Google was able to predict this drug, which turned out to be like helpful for cancer research. And then people went to the lab and actually tested that drug, and it turned out that this is working as intended, and it was proposed by an LLM, and that was not proposed by a human. So these sort of directions. There are some directions from this company called sort of periodic labs. There's this company called Future House. There's like an effort coming from like Google DeepMind, and all these different sort of efforts are out there to create like some form of an AI scientist, which is going to like utilize this sort of like whole sort of verification loop, very often like also including the actual physical laboratory where you will be performing certain experiments, collecting the results, testing a certain hypothesis, iterating on hypothesis, and so and so, in order to bring a new scientific discovery. And I do think that this is going to be the new paradigm of science. At least that it is not crazy to think right now that it is going to be the new paradigm of science for like a certain fields, like, and just in the matter of maybe, I don't know, 2 to 3 years. So it's coming, and it's, I think personally I find it very exciting.
It's certainly brain itching to a very in a very positive connotation. Especially that third point that you mentioned. Yeah, but okay. One final aspect then. Uh, since I study a lot about AI risk, governance, and security, that side of these autonomous systems and infrastructure, in your opinion, how do you see, or are there any implications in whatever way, ethical, moral, etc., societal implications that you see have very high potency in materializing in regard to both AI led scientific discoveries and AI assisted scientific discoveries?
Yeah, so I'm definitely not an expert on like ethics,
Hmm.
or especially on how this like how something should be like regulated by the government, or like what will be the implications of it on the society. But one thing I can say is that when I'm thinking about this, I'm trying to like look at it through the pretty positive lens on this. That you know there's a lot of science to be done, and we have a very limited number of scientists. Scientists, like the training of a scientist takes a very long time. Typically, starting from sort of from an undergrad, that's at least like, I don't know, 10 to 12 years to produce a professor, right? Which is a pretty long sort of timescale, which to some extent is necessary to make a mature researcher. So this is like not very efficient. Also, researchers in themselves are like not best at communication in many cases, which makes things also to not be very efficient. And I do think that there is like some merits in just being able to do some science, like not necessarily all science, but like some parts of science, especially like the more laborious parts, like the things which we kind of know how to do, but like there are many caveats, and like they're laborious in a sense of like requiring like a lot of effort and just like sort of like time span, but not necessarily like plenty of sort of like skills unique to humans. I would want to, sort of like outsource some of this work to AI, and then be able to, instead of, multiply, this effort by like whatever the number of scientists available, I would want to have these like AI scientists who can, explore so many more directions. And like, even, if these systems start working, then you can deploy, I don't know, like dozens of thousands of these agents, for instance, right? And then try to explore many problems in parallel. And even if they're worse than humans are, right, then still there might be like a multiplication of sort of research effort. Even if they were like 10 times worse, then still you'll be able to like, I don't know, put out like 1,000 more of like research effort than, you know, a small number of like human scientists would be. So this is like what I would find beneficial. having said that, and I should mention, like, when we can parallelize this research, then perhaps like we can, answer many of the scientific problems sort of much more quickly. That thing can have like a very direct positive benefit on the well-being of humans, right? For instance, like, if we managed to find like better materials for certain important tasks, like sort of sending in the electricity at like lower costs, or so, by sort of trying to find like materials which are just better at it, like whatever, like superconductors or something, which would work at like high temperature. Then I do believe that we can benefit the society quite a lot, and if we can benefit from an AI scientist in that direction, that would be amazing. Having said that, I think that there are many risks which one needs to be sort of aware of. Like, some of them lie on the level of just the flagship models, and then this is the, I guess, the responsibility of the companies which create these flagship models to sort of be careful about the AI safety as well, perhaps as of like governments to sort of be able to like regulate that and make sure that like we're able to control it to some extent. But again, I'm not an expert on this, so it's hard for me to say more about this. Um, but at the same time, just on the science side, I do think that like we should be very careful about what are really the tasks we are trying to solve, and sort of like what potential implications they might have, and this is an important thing to keep in mind. And this is like not so specific to just the AI scientist. It's just that if the AI scientist becomes true, then sort of will be just able to do much more in a much shorter time scale, and because of that, like the entire sort of like time scale accelerates in a sense. So this is like
Hmm.
one new aspect to this. So I guess that this is what I would say. Like, I would still think, and I would still be very much hoping that the potential benefits are going to be way bigger than the potential risks. But like I said, like this sort of turns on the clock to be like even sort of faster paced. So because of that,
Hmm.
we need to also be able to like think about the ethical implications of what we are doing at a much shorter time scale. I think that's one of the main innovations like coming from this like AI scientist direction. If that direction again, like if that direction works out.
I do believe that with exponential such technologies who follow this overtly exponential growth path, a sort of liability becomes that you have to get it right each and every single time, and you only have to get it wrong once for all of it to just collapse down. And with AI, I really do endorse for now the dynamic, the Stark and Jarvis dynamic, where you as you said, you're able to funnel down these calculations to whatever extent they may be. They may be even they are novel calculations, right? There isn't any pre-context to it. I'm not adding any prompt or so on and so forth. I've given you the lab reports. You know them. Now just run as many test cases as you can and just give me the results of the best ones. And maybe that is something that is a lot more transferable currently in that positive connotation that you highly emphasized upon. So that is one way that can really be transferred into the current demographic of reality that we follow and live in. But okay, then maybe the last and final segment and the question to you, Dr. Dominic, what would be your word to humanity at large?
Okay. Yeah. Yeah. Okay. This is a big question. I think I think one thing I can say, which I think will remain to be true, is that what makes us as humans to be very successful, um, is the ability to sort of continually learn, and and in a sense like continually adapt to new circumstances. And I think that this is, one of the important things which will remain important and which we should really embrace in us. And this is also one of the things which is, sort of getting perhaps a little bit killed by, sort of the advent of like large language models, that we're really starting to like outsource a lot of thinking to these models, and sort of really losing the capability of like to understand certain things. And I do think that it's still very important to be able to continually learn and like quickly learn new things. And apart from just like sort of day to day human kindness, and sort of really wanting to understand other human beings on a on a deep level, and sort of genuinely appreciate them, like I think this continual learning is something which will hopefully make us even more successful as a civilization, and just make the world of everyone to be better. But we'll see. I mean, hopefully future will pan out the way we want, and it'll be even nicer to be human being in the future. We'll see.
Always good to be colossally hopeful. Like never really hurts. Dr. Dominic Kufel, thank you so very much for having this conversation. We touched upon a lot of aspects, symmetry and structure in physics, artificial intelligence, limits of computation, so on and so forth, interpretability and scalability, intuition, building intuition, instilling intuition, humans and AIs in this entire scientific endeavor of research that we have a part and parcel in, and maybe a lot of practical research anecdotes and pathways that a lot of younger chaps will be able to take a lot of with them. So genuinely, thank you so very much for this entire episode. I'm really
Yeah,
really
thank you so much
hopeful
for
that
having
people will
me.
be able to take a lot of benefit out of it. Thank you.
Yeah, thank you so much. Yeah, it's been great. Thanks.
Okay, so